Every time I generate text with a large language model, it feels like waiting for paint to dry. The tokens just tick out one by one, slowly. Is there a way to speed this up?
That's exactly the problem speculative decoding aims to solve. Think about how transformers typically generate text. It's a fundamentally serial process, token by token. That's a bottleneck. The paper highlights this directly. Decoding K tokens takes K serial runs of the model. Each new token needs the previous one as context, so you can't just generate them all at once.
Right. We built that intuition for transformers in case TCM 123005. So how can we make something serial faster without changing the core model?
This is where speculative decoding, an algorithm to sample from autoregressive models faster, comes in. Imagine you're writing, and you have a very fast but sometimes wrong assistant who suggests the next few words. This assistant is like our small, fast draft model. It's quick, but unlike a human assistant, it's predicting based on statistical patterns. And crucially, unlike a human editor, our main model can check many of its suggestions simultaneously, not just one by one. That parallel processing is where the analogy works, but human editors are usually serial.
Okay, a fast assistant, but I'm the editor. I'd have to check every word they suggest, one by one, right? That doesn't sound faster if the assistant is often wrong. If this assistant is sometimes wrong, does that mean the final output changes? I don't want my LLM to generate faster but give me lower quality or different results.
That's a crucial point. Speculative decoding guarantees it works without any changes to the outputs. The final sequence is always identical to what the main, larger model would have generated traditionally. The paper makes two key observations. First, hard language modeling tasks often include easier subtasks that a smaller, faster model can approximate well. That's our assistant.
So parts of generating text are actually pretty predictable, even for a smaller model, like common phrases or grammatical structures?
Exactly. The second observation is that by using a novel sampling method, we can, quote, make exact decoding from the large models faster by running them in parallel on those approximated outputs.
Parallel verification. So the editor, the big LLM, isn't generating, it's just checking several suggested words at once. That's clever.
Exactly. The editor analogy highlights the validation role. But remember, the LLM editor checks batches of suggestions with statistical precision, which is different from a human reading through text sequentially. Yes, potentially generating several tokens concurrently. This is like our bottleneck then reconstruct pattern from previous episodes, but here it's draft then verify to unlock parallel processing.
So the large model still has the final say, but it's checking batches of tokens instead of generating them one by one. I can see how that's faster.
And critically, this can accelerate existing off-the-shelf models without retraining or architecture changes. It's an inference time optimization, not a model change.
That's powerful. But how does this draft and verify mechanism actually work under the hood? What are the steps? And what happens if the smaller model makes a mistake?
In practice, this technique is often called assisted decoding, as Hugging Face labels it. The small, fast model is called the draft model, or assistant model.
So the draft model tries to predict, say, 5 tokens ahead given the current context?
Exactly. Let's say the main model has just generated "the cat sat on the." The draft model then tries to predict the next few tokens, like "Matt." "The dog ran."
It's like a very advanced predictive text feature, but for the LLM itself, suggesting several words rather than just the next one.
Yes, it's similar in the sense of suggesting completions. Where it differs is that it's proposing a sequence of tokens, and the main LLM then has a specific fast protocol to verify these proposed sequences with statistical rigor, not just a simple accept-reject heuristic. Then the large main LLM takes the original context, the cat sat on the, plus all those predicted draft tokens. It processes them in parallel to verify their probabilities.
Processing in parallel is key. The main model doesn't generate them itself, it just gives a thumbs up or thumbs down to a whole sequence of proposed tokens.
Specifically, the large model performs a single forward pass over the entire sequence, original context plus all proposed draft tokens. This gives it the true probability distribution for each proposed token conditioned on all preceding tokens in the full sequence, all in one go. Then, for each predicted token from the draft model, the main model compares its own true probability for that token against the draft model's probability. Based on this ratio and a random number, it decides whether to accept the draft token. This is where the novel sampling method from the paper comes in, ensuring the final output's distribution is identical to what the main model would have produced normally. If the main model confirms Matt is highly probable given the, and the is probable after Matt dot, it accepts both. If dog is improbable after ran, it rejects dog and all subsequent drafts.
So it accepts a prefix of the draft that is consistent with its own probabilities, and then it generates the next token from that point itself, if the draft was rejected. What if the draft model is frequently wrong? Does the overhead of checking and rejecting negate the speedup? It sounds like it could be inefficient if not tuned well.
That's a good question. While verifying is faster, there's a trade-off. If the draft model is too frequently wrong, the main model ends up rejecting many tokens, falling back to generating token by token for longer stretches. In extreme cases, a very poor draft model could even slow down generation due to the overhead of the failed speculative steps. The best speedups, like the 2x to 3x acceleration observed in the original paper, happen when the draft model is reasonably accurate and well aligned with the verifier.
The efficiency gain comes from the main model's ability to accelerate decoding by processing multiple tokens in parallel. A single forward pass of the large model can validate several draft tokens.
So we're swapping many small forward passes of the main model for fewer but wider parallel validation passes. The big LLM still sets the quality bar.
Hugging Face's Transformers library implements this directly through its generation mixin class, which handles various generation strategies, including assisted decoding.
So this isn't just a research idea, it's something I can use right now with models I'm already familiar with?
Absolutely. You enable it by passing a draft model argument to the generate method, or using the assisted decoding pipeline. The library handles the complex orchestration for you.
It's amazing how these foundational ideas from research quickly become practical tools accessible to everyone.
This can dramatically speed up decoding for large LLMs, often by 2x to 3x acceleration, as shown in research, especially when the draft model is well matched to the main model and the task. It's ideal for latency-sensitive applications like chatbots. One practical consideration is that this approach requires loading two models into memory, the small draft model and the large verifier. While the draft model is small, it still adds to the overall memory footprint, which can be a limiting factor in some deployment environments.
I can see myself reaching for this when I need faster responses from a high-quality model without compromising on what the model actually says. I'm Maya. Thank you for thinking this through with us.
I'm Archon. Another idea in 3 hours. Take care of your mind.